Good afternoon. My name is Reinhold Mann, and I'm the Deputy Vice Chancellor for Research at the University of Tennessee here in Chattanooga. It's a pleasure to welcome you today to the first of a series of 3 lectures we have scheduled this week on various topics on quantum information science and engineering. What triggered this series of lectures was the recognition of World Quantum Day, which was on April 14, this past Friday. And we're part of a community effort which is also labeled under the motto of Gig City Goes Quantum. And there's a website you ought to go to get a lot of good information on the events that happen around Quantum Day this year here in Chattanooga. Our goal was to have about 1,000, actually it's exactly 1,000, we may not get there, but if you don't set goals, you don't move forward. So we have the goal of having 1,000 learning events related to quantum science and technology. And so I think we're making good progress. We're working closely with EPB and Qubitech, and as part of that work on deploying the first commercial quantum network, we're looking forward to having a quantum node on campus in the July timeframe this summer, which will be an enormous asset for us and the community, and by community I also mean the technical community worldwide, to have access to this network. And we're looking forward to a lot of experiential learning opportunities to bring, to basically get students involved, faculty involved, and get commercial partners involved in this as well. But today we're going to hear specifically about a topic which our speaker will introduce. And what I want to do is introduce Dr. Rayfield Powell to everybody. He is a distinguished research scientist at the Oak Ridge National Laboratory. It's about 90 miles north of here. He's been working with us, helping us think us through some issues of curriculum development and experimental design. But today he's here to talk to us about quantum computing. Dr. Powell got his undergraduate degree in physics from New York University. He then went on to get a degree, a PhD degree in engineering physics from the University of Virginia in Charlottesville. And after a postdoc at NIST, he came to Oak Ridge National Laboratory as a Wigner Fellow. The Eugene Wigner Fellowship Program at Oak Ridge is a very prestigious fellowship program which was named after the first scientific director of the laboratory in the late 40s, Eugene Wigner, who got a Nobel Prize in physics in 1964 for work that partially also was related to the Manhattan Project. Anyway, so he was a Wigner Fellow at Oak Ridge National Laboratory for 3 years, and then came on as a staff member and moved up the scientific ladder at the laboratory. He has over 150 peer-reviewed journal publications, and his impact factor, which is also measured as the H-index, is significantly high. It's in the 30s. He has led or been a member of teams who captured significant amounts of extramural funding. The figure is around $45 million over the last 10 or so years. And he's also been a mentor to students and postdocs during his tenure at the laboratory. And that amounts to impact on over 30 to 40 careers. So it's a pleasure to welcome Dr. Powell, who will talk to us about quantum computing.
Hey, thanks. Okay, thank you very much, Reinhold. So yeah, my name is Rayfield Powell. As you can see on the slide there, I'm in the Quantum Computing and Sensing group at Oak Ridge. So I actually founded that group, but I'm not the current group leader. We have a great guy who's our current group leader there. And so yeah, we kind of have, I guess, 2 heads. And so that's why the group is named Computing and Sensing, because I'm pretty indecisive and I want to do both quantum computing and quantum sensing, so that's what we do. And that's why, as Reinhold mentioned, I got a PhD in engineering physics, because when I was younger I couldn't figure out if I want to do engineering or physics. So I happened to have a degree at one of the schools That's called engineering physics. I figured that sounds, that ought to be interesting. So yeah, okay. So I'm here to talk about the quantum computing and this. I got this subscript here, second quantum revolution. And if you're anything like me, and by the way, I'm a quantum physicist. That's my job, quantum information scientist. When I heard there was a second quantum revolution, I was like, what was the first one? So the idea is, yeah, the first one was when we discovered, we pretty much worked out quantum mechanics around the turn of the century, and it was being argued about a lot after that for quite a while, still being argued about a lot. So the second quantum revolution is when you actually use quantum mechanics to do useful things. Oh, hold on, let me set myself a timer here. So by useful things, I mean like computing or sensing or networking or something else. So one of the jokes I like to tell is about a time I was putting papers up online. You can put your papers on this thing called the archive, and every now and then some news websites will go look around for interesting papers and publish news stories about them, and put the ability for people to put comments on those news stories. So somebody had found a paper of mine that does a quantum sensing, and did a news story about it, put it up online, and he ended the news story with like, I don't really understand any of this. Can anybody help in the comments section? And a guy jumps in the comments section and says, yeah, this is just the quantum stuff. Those quantum guys, they just put the word quantum in front of everything. You got quantum computing, quantum sensing, quantum networking, quantum scrambled eggs. So, and I joined in the comments. I was like, well, yeah, pretty much. That's what we do. But there's a couple of complicating factors. So I'll tell you a little bit about what this. Okay, this pointer doesn't work too well. What this second quantum revolution means. But first, two small bits of history. So first bit of history, where I'm working right now at Oak Ridge National Lab. You guys probably know, played a major role in the Manhattan Project to develop nuclear weapons. This was the first continually operating nuclear reactor. So the lab, I mean, this picture, this photo, this is what the lab used to look like. It's come a long way. So what the lab really evolved into around the turn of the millennium was something much more diverse, much more basic science, fundamental science first. And the lab developed a real, I don't want to, the word obsession is not the right word, but a strong interest in computing. And so over the years, they've been working to build the world's biggest computers, world's most powerful computers. And one thing you could ask is like, why? Why do we build computers? So the reason why we build computers like this, there are two reasons that there's plenty of reasons, but here's two big ones. So first one is we want to answer scientific questions. So we have some scientific knowledge that we want to gain. We don't know how to crunch the numbers ourselves. I mean, in principle we do, but it would take too long. And so we program a machine to crunch the numbers for us, and it happens only polynomially faster, but quite a big exponent in the polynomial. And so the other reason is, of course, industry. Industry wants to answer scientific questions, but they also want to answer questions that will help them, let's say, make the world a better place and make some money at the same time. So, of course, another thing that these machines are used for a lot, back into that make the world a better place category, is trying to figure out what's going to happen with climate change. So there's a lot of climate calculations done on these machines. So here's a little bit of history about, these are 4 of the last supercomputers at Oak Ridge. This is not an inclusive history of supercomputing in the United States or in the world even, okay? But this is just a sort of self-serving history about supercomputers at the place that I happen to work. So when I got to Oak Ridge around 2009, this guy was up and running, Jaguar. And yeah, so Jaguar was actually served as the first OLCF machine, Oak Ridge Leadership Computing Facility machine. And so it peaked, it was upgraded a few times. It peaked at about 2.3 petaflops. And at the time, just thinking back on it, I mean, it's only been, what is 2022 minus 2009? It's I think 13 years. it's amazing the distance that we've come in 13 years. It's just crazy to even think about. So I think the vertical scale on this, this slightly increasing, this line here, isn't quite right. But anyway, so Jaguar was succeeded by Titan, and this machine introduced a new model of computing called, it introduced this accelerated supercomputing model. Obviously, it didn't introduce the model of accelerators, though I was already using accelerators to play games before Titan was even in conception. But some folks decided to use GPUs for something besides playing games. And so they did a lot of AI with this thing, which of course, so spoiler alert. I'll talk about AI a little bit. I did not, however, use any AI device to help me write this talk. I didn't use it to make pretty pictures either, and I should have, because there are no pretty pictures in this talk. You can just go ask it, show me the picture of a supercomputer, and you'll probably get something that looks cooler than this, but it won't be accurate. So anyway, so this guy used, 8.2 megawatts. It had a bunch of NVIDIA GPUs in it. And so that was crunching for a while, up until 2017, when Summit came out and had a huge leap, 200 petaflops. And what's really interesting is the energy. They managed to keep the energy use pretty low. So that was really interesting. Okay, so now we have Frontier, which is the world's fastest machine according to the top 500. And let's see, this is the only one I decided to put stats on because the talk would go on too long if I keep giving you the whole entire history of classical computing before I get to the quantum computing. So let's talk about the stats of Frontier, but they're kind of mind-boggling. Okay, so you got 9,472 CPUs, which actually those are multi-core CPUs, so 600,000 CPU cores and over 8 million GPU cores, which is just crazy. The thing that really blows my mind, though, is the file system, read-write speed. So I almost wonder if that was a typo. 75 terabytes a second. I mean, that's like many orders of magnitude faster than the RAM in my desktop computer. So it's really funny because, if you work with computers at all, you're kind of like, oh, you want to keep things in RAM because hard drives are too slow. And so this is flash memory, which is pretty fast. They've got a bunch of NVMe, which means non-volatile memory, attached to each of those cores. So this is the state of the art for classical computing today. And so they're doing AI on it, of course. They're doing climate models on it, of course. There's a lot of biological computations, just kind of anything you can think of when it comes to answering basic science questions. So me and a bunch of other people have been thinking, what do you do after this? Well, you go to more exaflops, right? What's the next thing, if you can't scale these machines anymore? So there's something interesting about the energy use. It is going up, although the change in energy is really, you've got to hand it to them. So at some point, the energy usage is going to go out of control on classical supercomputers if we keep scaling them, unfortunately. So Dennard scaling, if you've heard of this, this is the scaling law for power per square centimeters or per surface area on chips. We used to be able to rely on power dropping with every process node. And the idea is that at some point, well, we've actually already sort of reached the point where power has stopped dropping with each process node. So one of the reasons is because the chips, we keep clocking them higher, right? Even when the process node shrinks, we do want to also clock the chips higher and build more cores in. And all of those things added together, we've started to kind of plateau on our power usage. And so what that means is we're going to hit a wall eventually and not be able to shrink things anymore and not be able to keep decreasing power as a function of as the number of cores increases, which leads you to a question about, what's the biggest classical machine we can make? So that's what I mean by what's next. And I don't know the answer to that, and I'm not going to pretend to claim that I know the answer. Just 5 years ago, there were people saying, well, you probably can't make things smaller than 5 nanometers, and there's a 1 nanometer node already mapped out. I don't know if we'll actually get there, but we do plan to make 1 nanometer wide transistors. So those things are going to have a lot of quantum mechanics going on in them. But so ignoring that, what is beyond exascale? So what I'm going to talk about is a different kind of computing that ostensibly, well, actually it's not obvious, but it should not be limited by energy consumption in the same way, because one of the ways to get rid of this increase in energy consumption as you increase the number of processors per unit area is to go away from the von Neumann model. Which von Neumann model is, does anybody know what that is? One person does. Okay, so I know people know what this is. So I'll tell you. Okay, it's when you've got execution memory and program memory separate from one another. Okay, so I don't have, like I said, I don't have a lot of pictures. You just have to rely on me moving around a lot. So like you got a processor over here, like an Intel, Pentium. Sorry, they don't do Pentium. Core i7, Silver Lake. I remember when I was a kid when the Pentium 3 came out, and I couldn't afford it, so I got an AMD K62. Just so but anyway, so you got a Pentium over here, and it's got cache, and then you have a bus, and then the bus leads to some hardware, graphics cards and stuff, but also to the memory, to the RAM. And so the RAM is it's a bunch of bits that are stored and they're constantly refreshed, and the processor says, I need to get something out of RAM and bring it into my cache so I can actually load it into registers and then start executing instructions based on the data that's in those registers. So the memory gets some electrons come down to the memory and ask, hey, what's stored at this position in the memory? Over here I got a whole bunch of rows and columns of bits, and they say, okay, it's this. A bunch of electrons move back to the processor. Now, it's not exactly like that. It's drift current, so this is electronics, right? But to move that information takes energy. And so the von Neumann model, which separates execution from memory, from data memory, requires a lot of energy to move the information back and forth. That's one of the main energy draws. But even the processor itself, we put the memory close to the processor, but the processing doesn't actually happen inside and on the bits, right? Instead, the information is read out and propagates through a pipeline of switches. It's basically a glorified counter, if you guys know about. If you built one, as I did in undergrad, actually I didn't do that great a job at it. We had to build a bunch of counters in our electronics for, I think it's called electronics for scientists. You make a bunch of counters. And the professor said, okay, now that you know how to make counters, let's do a processor. Let's all build a processor now. And yeah, it's kind of a big leap, but it does allow me to say crazy things that might offend people like I just did, that, hey, processors are glorified counters. Okay, so, so an interesting thing that is not illustrated or said on a slide anywhere in this talk is what I just said, that quantum computers actually do not use this kind of a model, this separate data. And now there are proposals for such, right? But that's not the leading dominant way to do quantum computing today. Okay, so let's back up. First talk about quantum information science. Okay, let's talk about information. So this thing I just told you about with the electrons moving back and forth and stuff actually kind of brings to mind the idea that information is physical, of course. So information is a weird thing. It's at least to me, it's not weird to guys like Claude Shannon, but it's weird to me in the sense that we're deriving semantic meaning from the state of physical systems. That's what information really is. And so, as you all know, computers themselves are state machines. The first computers you could actually look, they were mechanical objects. And you can see we're just like, almost like a Rube Goldberg machine where we drag a pendulum and let it hit something, and what's the state of the whole system at the end? That's our computation. Computers are the same. They are that still. That's what a computer is. It's a machine that you encode the information that you want to know into one type of state, the starting state, the question, and then you let all the switches, the logic switches that I was talking about, react accordingly to what the stuff you input on the starting state was. You read out the ending state, and that's your information. That's your answer to your question. So information is physical, and it really just depends on the meaning that we impart to it. That's an interesting point. So that said, that sounds arbitrary, doesn't it? But it's, there are some limitations, the laws of physics. So you have to abide by the laws of physics when you encode information into something. Why is that? Well, because we are, we live in the universe. So this is kind of what kind of a tautological point is that to make? But it's important to understand and realize when you consider what is the total breadth of what the laws of physics contain. So the idea being that back when these guys were doing classical information theory, Shannon, Turing, anybody know who that is? It's Newton, yeah. I don't know if that's what he actually looked like. It's a drawing I found on the internet. So the laws of physics that determine what information is and what you can do with it was classical physics. And so that leads you to build Turing machines. That leads you to build state machines who obey classical physics. And that's why you can make a mechanical object that's just a bunch of pendulums swinging back and forth. You can make that into a computer. It just has to obey classical physics. It has to be a state machine. And, oh, hold on, let me go back. It has brought us some really, this classical physics has brought us basically to where we are in the world today. So pretty good. Computer science as we know it, cryptography, math, put game theory in there, but honestly, you know, this one seems to be good mostly for making money. These are really good for science. No, I'm just kidding. Sorry. Do not, I forgot this thing is live, about to get canceled by game theorists. This one is actually really good for a lot of things too. But anyway, so that's the only one and only time I'll apologize to you game theorists. Okay, done. Let's move on. So the laws of now, what if you expand the laws of physics beyond classical? You got quantum physics now. Quantum physics really says what you can do with information, not classical, because classical physics is a subset of quantum physics, turns out. Okay, great. So the thing about quantum physics is that there are these weird rules, superposition, entanglement, uncertainty, which I will talk about. And I figured I would talk about these things because I think this is the first talk Reinhold was saying, so we're not going to, I'm barely talking about quantum computing, to be honest with you, because I'm taking way too long, but we'll talk about it a little bit. So in the quantum physics domain, I put optics in there. That's just because optics is special for me. Superconductors, atomic molecular physics, we got material science. So like these days when you do material science, it's all at the quantum level, you know. So even guys who don't call themselves quantum information scientists like me, a lot of people are doing quantum physics. So who are these guys over here? You got Einstein, Schrodinger, and, oh, sorry, Einstein. Can we edit that out? Einstein, Schrodinger, and Heisenberg. So, and by the way, I'm terrible with names. I don't know if that's, you know, how you say their names. My name is Rayfield. I had a long, hard life of teaching people how to pronounce my name. And so it's a great irony that I am terrible at pronouncing people's names. Some people come to me, isn't his name Schrodinger? And I'm like, I don't know. I just, Schrodinger. So the nexus of these ideas, quantum physics and classical physics and quantum physics, is where quantum information science lays. It doesn't lie. Quantum information science will never lie to you. But quantum information science lays right there in the nexus between those two things. And basically we're just, exploiting these two things to do interesting things, sensing, communication, and computing, like I told you before. And one day, making scrambled eggs, I guess. So, all right. What is the second quantum revolution again? So it is using these two things to do these things. So I've spent, let's see, probably, I guess 60% of my, let's go with 58% of my career doing this, 31% of my career doing that. No, 21 and 21. Does that add up to 100? I always go for extra credit, so if it added up to 105, that would be fine. So I've done a lot of quantum computing. Oh, you can barely see this. Done a lot of quantum computing in my day, done a lot of quantum sensing, a little bit of quantum communication. So I'll define what these things are in a minute. I think starting on the next slide. But to me, just quickly to say, I think these are sort of the two very key things that enable all of this QIS stuff, all this quantum information science stuff. These weird quantum concepts that don't have classical equivalents. Now, superposition, if you know about partial differential equations and you know about the general solution to partial differential equations, then this is the basic, on a basic level, same kind of idea. Quantum mechanics has superposition in it because of where the laws of the types of equations that describe the laws of quantum mechanics. And when you solve them, you find solutions to those equations that lead to superposition. But the interpretation of superposition is where it gets really weird. Right? Like it's easy to think about the superposition of electromagnetic field when you solve Maxwell's equations. And everybody who does physics, and I'm present company accepted if you didn't, that's fine because I'm going to explain it right now. Two electric fields can superimpose to make a bigger electric field or a smaller one, right? You can have solutions to electromagnetic field equations that consist of multiple solutions at once. We call that superposition. But in quantum mechanics, when it gets weird is like, well, what if I associate a particle with the solutions to those equations? What if I associate some kind of physical entity that I can actually get a hold of and measure? And you still have to say things like, yeah, but it's still in a superposition. And so people say things like, oh, qubits can be, you know, here I've got a picture of a spin, you know, it can be both up and down at the same time. You'll get that one a lot if you go look around on the internet. What does superposition mean? Another interpretation is that it has no definite value until you go and check. But this describes the probability of your finding, when you do go check, of your finding which state it would be in. And so this happens to describe a perfect superposition. So a particle that can either have its spin, which is an angular momentum. I'm going to go to something simpler in a second, pointing up or down. Entanglement is a different thing I'll talk about in a minute. So let's just finally move to the next slide. OK, so using those things to do cool things, what can we do? OK, imaging with greatly reduced noise. I think the second one, magnetometers and gravitometers. Has anyone ever heard of LIGO, Large Interferometric Gravitational Observatory? I think the L is large. I can't remember what exactly it stands for. But you know, in 2015, they actually found gravitational waves, which is pretty amazing. So right now, these things are quantum sensors actually using the concepts of quantum noise reduction, which is related a little bit to entanglement, to actually search for signals that you couldn't see classically with classical sensors. So that's pretty amazing. Communication, if you've ever heard of quantum key distribution, that's QIS enables that. This is when you just send a encryption key between two parties that's you can't eavesdrop on it. I'm not going to say unbreakable until the next point, which is when you use that key as a one-time pad, you have unbreakable encryption. So you have a quantum means to send an encryption key from point A to point B, and then if you then both use that to encode classical information, now you have an unbreakable one-time pad that you can continually refresh with a quantum channel. So that's a real thing. You can actually buy a product right now that does that. And there's been a demonstration here actually last year, in 2021, actually putting this type of encryption, this quantum encryption, on a power grid. So that was pretty amazing. And of course, computing. So I think, you know, without going through each of these one by one, let's just say, you know, for now our purpose is answering scientific questions, right? And there are some questions, it turns out, and you know, this is sort of I'm burying the lead. I'm just now telling you this like 15 minutes in. There are some scientific questions that classical computers cannot answer, unfortunately. It's not that they can't answer them in principle. They can. But we know that to answer some of these questions, it would take those machines, you know, if we had all the energy on the Earth dedicated to running these machines, still longer than the universe has been around to answer those questions, unfortunately. So we're designing these other machines that that can answer those questions a little bit faster. Not every question. You can't make a quantum computer doesn't do everything a classical computer does faster, just some things faster. So this is sort of the idea here, this kind of conceptual scaling here. These two curves here correspond to the amount of resources it takes to find the answer to some really hard problem, like an NP hard problem on a classical machine. And you can do a lot of things to make those things classical machines go faster. One of those things is increasing the number of cores, increasing the number of GPUs, increasing the clock speed, increasing the surface area and energy that those machines take. And I'm about to say something that will sound dismissive, but everything you do to make it go faster, what it's going to do is it's going to take this exponentially growing curve and shift it. It's going to shift it so that, okay, maybe you can do it a little bit faster, so it takes a little bit less resources to get the same answer, right? But you can never change the scaling. And so all of those computers I showed you on the other slide, with those 4 OLCF computers, each one is a move like this. And so if we want to find answers to those particular questions that are hard to answer, it's just not going to happen by building bigger machines like that. So the quantum version, the scaling for these particular class of problems, which I'll talk about those problems in a minute, is sub-exponential. And so the idea is that once you build a big enough quantum computer, there's some crossover point. There have been 2 ideas for crossover points in the history of quantum computing. And the first time I gave a talk like this, the first one had not been crossed yet. It was called quantum supremacy, a term coined by John Preskill. And that is when a quantum computer does a bunch of number crunching that a classical computer can't do. Nothing more. So in other words, think of like LinPack. Think about a benchmark that we don't ascribe any meaning to, any scientific meaning to, other than a measure of the performance of the machine. This crossover point has technically been reached already. So that was done by Google, a big team at Google, I think it was in 2020. And so that leaves another hurdle for quantum computers to cross, which is doing something useful. So yeah, this is a highly cited paper, but at the same time, it's sort of also kind of shrugged at a lot because by quantum physicists and classical computer scientists as well, because we know we have to cross that point on the way to doing something useful with quantum computers, and that's not to be dismissive of that result. I mean, it was really interesting to hear about what it took to do that. A lot of hand tweaking of quantum computing apparatus in the lab for many weeks and days and, well, years building up to that point. So now we're in this region where we're not quite here yet for useful problems. We're maybe, somewhere out here or something. And that second one they call quantum advantage. And actually, I guess there's been a push recently to sort of combine the 2 terms in something called quantum utility. So if you've heard of John Preskill, he's extremely well known in the field of quantum information. He coined that term quantum supremacy, and in a subsequent interview later, he mentioned that there had been a bit of a backlash against using this term quantum supremacy because it reminded people of racial supremacy type terminology. And so he said at the time, that's a really great point that I concede on, and it probably should be something like quantum utility, something like that. And so I think the term quantum utility is what's coming up and what we're aiming for quantum computers right now. But this sort of number crunching super performance over classical machines has been achieved, which is really amazing when you think about it. All right, so taking a break for a second about the potential. This is sort of about the potential of quantum computers. Taking a break from that for a second and talking about how they work. The most important thing to me, because it's my job, in quantum information science is quantum entanglement. It was the other one besides the superposition. Okay, so let's see. Let me just read this. Yeah, it's very important for quantum computing. The reason why is because it's involved in almost all useful quantum algorithms that we know of have to use entanglement at some point. And actually is the source of signal-to-noise improvement in quantum sensors. And it's actually the source of the theoretical proof of security in quantum key distribution. So entanglement is like the heart of quantum information science for me. And this is where it comes from for me. So this guy, did I get that name right earlier? Who's this guy? Anybody know? So Einstein back in, it's written right there. Okay, so I should read my own slides. Einstein back in 1935 wrote a paper. It said, can the quantum mechanical description of physical reality be considered complete? And that's supposed to just roll off the tongue. So, and of course, spoiler, why ask the question unless you had an answer that was going to be provocative? So they said, no, of course not. In their abstract, the last line of the abstract says, one is therefore led to believe that the wave function description of reality is incomplete. Why is one led to believe that? Because this. What is this? I'll tell you about it in a second. This and this, all this mathy stuff. What is it? Einstein said, quantum mechanics doesn't make sense because entanglement. because it predicts entanglement. So this paper for me is kind of, now it was talked about before. You guys heard of Schrodinger's cat, right? There's an actual analogy come up with by Schrodinger, which is that you got a cat in a box, you got a Geiger counter, you got an alpha particle source. If the Geiger counter detects a click, it will break a bottle with a hammer of cyanide in the box, and the cat will inhale it and die. And so since you had this alpha particle source, right at the half-life, you don't know whether the material, the radioactive material, has emitted an alpha particle or not. That's superposition. So you have a 50-50 chance of emitting an alpha particle at the half-life. But the cat state, sorry, pause for drama. The cat state is tied to the state of the alpha particle. And so the term entanglement was coined there to say, oh, you could think up crazy, ridiculous schemes like entangling the cat state with the alpha particle state, where the entangled state is something like this. Cat, state of cat, times the state of the alpha particle in one particular state in superposition with the other state. That state being, alpha particle emitted and cat dead. The first state being cat alive and alpha particle not emitted. So these guys said, well, that sounds crazy, and quantum mechanics is perfectly fine to predict that. And therefore, quantum mechanics must be bad. And so they envisioned this idea in the context of a thing called continuous variables, which is hard for a lot of folks to understand. Back in 1935, it was pretty hard for people to understand what this thing is. These are superpositions of particles whose position and momenta are correlated with one another perfectly. And they said, what if I took a particle, A and B, and I checked where it was, and I found it was at position X. Without having measured particle B, I would know it was at position X, and I could have done the same for momentum. And that doesn't make any sense. They call that entanglement, spooky action at distance. So this is the easier, so it took a while for people to digest this. In the 50s, a new explanation that didn't involve integrals was proposed, in which rather than entanglement consists of over a continuum of states like the life of all the cells in the body of a cat, let's just think about simple two-level quantum systems. So on or off. So I'm illustrating that here as light switches. This is off, this is on. And so the idea here is that this little multiplication sign here means that these two guys are in the same state at the same time. And the plus sign means that they're in superposition. These two states are in superposition with one another. So that's the interesting thing about this is you can't factorize this into two separate functions for either object. Let me go into more detail about it. Okay, this is a superposition. As we talked about before, superposition, means that you can be two things at once, as we like to wow people with sometimes, or you can have a totally indefinite state until you measure it. They're the same thing. It's the same. You can describe it however you want. Actually, Heisenberg uncertainty principle allows you to hide all philosophies about quantum mechanics within the noise of quantum mechanics. So, so you don't have to worry whether or not it was exactly one or the other or not. This describes accurately the probability of getting it one way or the other. That's guaranteed. Okay, so you can take that to the bank. I mean, I do. It's my job. So, sorry. Either on or off, that's superposition. What if I have two switches that are either on or off, but they don't have anything to do with each other? So, okay, I write that like this. This is a wave function, not normalized, for one switch, and this is a wave function for another switch. And this multiply sign means that there's a state on this side and there's a state on this side. What happens if I measure one of the switches to check if it's on or off? Well, I'm not going to get I'm going to get an answer probabilistically, like I've described to you before, but it's not going to depend on the state of the other switch. When I do a measurement, I find either one of the answers, let's say for switch A. Okay, switch B can still be in a superposition. It doesn't have anything to do with switch A. That's what this math right here is spelling out. But I can write, what I'm telling you about entanglement is, I can write down a superposition, a quantum superposition, that involves more than two quantum particles, more than two switches, that you cannot write like this, and such that when I perform a measurement on one of these switches, the whole wave function collapses such that both switches' state is now determined. So what happens if I do a measurement on switch A or B here? I'm going to choose one of these two, probabilistically, one of these two states. That's what the measurement postulate in quantum mechanics says. So if I were to measure A, A, there we go, and find that it was on, then I'm in this state. The quantum system is in this state. But the quantum system has two subsystems, and it means B is also off. So they called that, EPR called that spooky action at a distance, which is kind of scary. Turns out everything's fine. Quantum mechanics does predict that. It works. We do entanglement every day. And actually in 1981, 82, this kind of entanglement was actually measured and quantified. So it took a long time. And actually in the interim there in the 60s, well, first in the 50s, from 35 to 50, a guy named David Bohm described it this way. He said, this is much easier to understand than what EPR came up with. And then in the 60s, a guy named John Bell said, I got a test you can do to actually show if something's entangled or not. And then in the 80s, that was demonstrated. Then the Nobel Prize came out for that a long time later. It was, I think it was last year, right? The Nobel Prize for Physics, Seilinger and Alan Nespe and others. So, okay, yeah. So Einstein called this, the other way to think about it is non-local correlations. So entanglement is weird because it means that I can mess with A and something will happen to B. Nothing really happens to B. It's just that its state is determined by the state that A is in. It is strange. It's not something that can happen classically. It's a purely quantum mechanical thing, and that's probably why it's required to do most quantum computation. Okay, how non-local? Here's a little quick diversion. What if I get a switch and you get a switch, and you go to, looks like Hawaii or Japan? Yeah, Tokyo, there we go. And I go to New York. I've never been to Japan, so let's say I go to Tokyo, and you guys go to New York. And then you measure yours, and then I measure mine. You measure yours, you find it's on. You can actually tell me before I measure mine. You can be like, I bet you're going to get yours is on too, and then you can wow me. I go, whoa, how did you know this? And you could say spooky action at a distance. So all kinds of weird stuff happens because of this. There's this thing called quantum teleportation, which you've ever heard of that. It's actually used in a form of quantum computing. The existence of the term quantum teleportation is probably one of the reasons why I got interested in quantum information science to begin with, because if you're a kid, and by kid I mean like age 20, if you're 20, a kid, by my current age standards, that is definitely a kid. I'm 42, just so you know, just to let you know. So that's a long time. Anyway, I got interested in that because the teleportation had just been found like maybe a few years before I started studying quantum physics. And like, okay, the guys who came up with this term quantum teleportation, which uses entanglement to transmit information over long distances, they say, oh, we probably shouldn't have called it teleportation. That's bad. It sounds like Star Trek. I don't know. Could have gone either way. I might not be doing quantum physics if they didn't go Star Trek with it. So let's, Anyway, sorry, you guys. Okay, back to quantum computing now that we've had that digression about entanglement. What does all this get you? The superposition and the entanglement. Why is quantum computing supposed to be so good? Okay, well, let's think about a bit. Okay, quantum bit, classical bit. Like I told you before, the quantum bit, which people call qubit, I've probably been saying that term without ever having defined it for you, is just a quantum bit. They could either be 0 or 1, each of them, right? Okay. But because quantum bits can exist in superposition, there's a little bit of extra complexity to the state space that this state machine can occupy already. It's kind of interesting. Now, when I do a measurement, the complexity is reduced. I'm either going to get 0 or 1. So I got to design my algorithms in a really smart way to take advantage of that complexity. Okay, but then if I have 3 bits or 3 qubits, things start changing. So this is the total surface area of state space that 3 bits can occupy. So you could think of any combination of on and off between the 3 bits here. But the state space of the quantum computer has actually grown by 30% of the surface area of the available state space by adding a bit. And I go to 10 qubits versus 10 bits. So and so I didn't do 100 because actually I made the original version of this talk before you could ask I could just ask for a picture now from like Stable Diffusion or DALL-E, but I handmade this picture for you guys. Otherwise, I'd be like, ask DALL-E, like, what do you think 100 qubits looks like? It would probably come up with, I'm going to do that later. You guys should do that now, those watching online. Let me know what you find. Anyway, so, it looks big, much bigger than that. So you can kind of get the semblance for, where is this, what's the source of this kind of exponential, sub-exponential scaling of resource requirements for the complexity of the problem. We have all this complexity that comes into our system that grows exponentially as we add every bit. So that is really interesting. That's what quantum computers are taking advantage of. But here's the thing. You can't take advantage of all this complexity without entanglement. So those are the two things that superposition and entanglement get you. OK, so what does that enable? And now we're coming to the end here really soon. And you can ask questions after that. OK, when I look at what I wrote here, it's very drab and boring. So let me just tell you, we're using, so what are people using quantum computers to do right now? Because people are actually using quantum computers to do stuff right now. Probably should have mentioned that at the beginning. You can go and use them right now if you want. You can go to, got quantum computers available at IBM. I'll have actual pictures of them in a second. Google, Honeywell, I think it's called Quantinium now. A company called IonQ. There's a company called Xanadu. There's a company called PsiQuantum. There's a company called Oxion. I mean, I've ran out of fingers. So there's a lot of quantum computing companies out there. And they're using them to do a few key things. Chemistry. People are looking for designing chemistry for a few key things. One of them is batteries. Another one is, so that's pretty important these days, prescription drugs. So looking at protein folding and that sort of thing. And a big one, before we talk about all these money-making ideas, okay, we talk about save the world kind of ideas. So this is a big one here. Anybody ever heard of Bosch or Haber? Again, bad with the names. Fritz Haber. Anybody? Bosch-Haber process. If you haven't heard of Haber, go look up the Wikipedia page. This guy had a really interesting life. He was making chemical weapons during World War I, and it's a source of most pesticides today are sourced in the research from Fritz Haber. Because, what do you do with a chemical weapon that isn't good enough to kill people? Kill insects with it. Yeah, it's pretty bad. Pretty bad. But this guy, along with Bosch, so Haber came up with this process that feeds the world. Okay, so on one hand, come up with this nitrogen fixation process to feed the world. On the other hand, try to come up with weapons that kill people. Then Bosch, and that's not to be judgmental. Go check the Wikipedia page. Very interesting life. And then Bosch, perfected and factorized it. Factory made it easily mass producible. Okay, so the idea here is that we want to find ways to do this that are more efficient than what we currently use, because it takes a lot of energy to make the stuff that we use to make our food. It takes a lot of energy to make fertilizer, in a nutshell. And so, okay, you probably will recognize this from either, sometime in undergrad, you saw some chemistry, or you may be an actual chemist, in which case this is child's play to you. But this is a chemistry equation, a rate equation, right? Well, it's not a rate equation. It's just this reaction. It's a reaction equation. These things go to this stuff, and this is the stuff we use to fertilize in fertilizer. We use it in fertilizer anyway. So the goal is to find energy at which this reaction can take place that is lower than where we currently have to put it. So currently it takes, 5% of the global natural gas supply and 2% of energy production. And that may not seem like a lot, but we got like 8 billion people on the planet. What's going to happen when we got 50 billion people? Now you got food production competing. Remember those computers? And if we want to build a computer that's going to take all the energy of the world to solve some big problem, it's going to be like a snake eating its own tail. You can't do. In other words, we're probably not, at least as far as we know right now, going to end up with a drastic reduction in energy cost with a solution provided by a classical computer. So this is one of the big selling points. But there's plenty of other things. Cybersecurity, code breaking, of course, that makes a lot of people scared. but don't worry, we have quantum key distribution. So quantum computers turned out to be really good at breaking RSA encryption. That was actually the first, let's say, widespread, like widely known important quantum algorithm. There's plenty of quantum algorithms, but Shor's algorithm, the one that breaks codes, was the one that, okay, we better look into this stuff. Okay, so here's some pictures of quantum computers. This is a superconducting chip. May not look like much. There's a few qubits on here. There's like 4. Here's a trapped ion system where these glowing little dots here are actual ions of ytterbium suspended in space in a vacuum above a gold-plated chip. And it's like, okay, I'm going to have to stop soon so you guys can ask questions. But that's kind of mind-bending. This thing's a computer. And it's actually used at 3 of those companies I mentioned use this technology. IonQ, Quantinium, and the X-ion, and a few. There's probably other quantum computer companies I don't know about. But these are ions. They're atoms that have lost an electron, and they're just sitting there in space, and they move around. And we check the state. Again, it's a state machine. We check the state of those ions, the quantum state of those ions, to find the answer to our problem. The superconductors are every bit as impressive. In fact, it's the superconductors that have been where the quantum supremacy experiment I told you about was done. This is another superconducting chip. You know, if you Google, back in the day, I used to say if you Google superconducting quantum computer, you'd find a bunch of pictures of Google's superconducting chips, but I can't even remember anymore which of these is from Google and which of these is from D-Wave or one of these other superconducting chip companies. Interesting thing about quantum computers, and the reason why we study them right now, even with classical machines, is that we can pretty much reproduce everything that quantum computers can do right now classically. Even that supremacy experiment I told you about has been reproduced, and actually the complexity of it has been reduced. It went down from 10,000 years to reproduce the quantum result to a couple weeks, down to finally to a couple hours. Still not as fast as the quantum computer, but we can study what quantum computers can do with classical machines right now. So that's been a lot of my job. And we've been wrestling with questions like noise, the connectivity. You can see this guy looks hardwired. How do you get the qubits to be entangled with each other when they're literally soldered down on a chip? You can do it, and we do it. But it's, you know, these are hard questions. And one question I've been wrestling with for 5 years up until 8 months ago, when I stopped working on that project, was how do you measure the performance of these things? And you know, that is a whole entire science unto itself. How do you tell when this guy has finally passed the quantum advantage / quantum utility benchmark? Well, you got to make a benchmark, and it's got to be something that makes sense. So that's all about, you know, how do you encode semantic meaning into quantum computers? How do you efficiently extract it at the same time using entanglement and superposition to manipulate the information? Yeah, it's a hard problem. So we really don't know fully what quantum computers are good for, but coming back to what I mean by that is we don't know the complete set. We know the things I told you about before. It's good. They seem to be good at certain chemistry problems, seem to be good at code breaking, optimization, and that's where the AI stuff comes in. So I actually didn't talk about AI much, but you can bet that before ChatGPT and company were out, I was going around giving talks, and one thing that I would say is that one thing I was doing with quantum computers was optimization, decision making based on optimizing over a neural net, where you store the neural net on the quantum computer. It's kind of mind-boggling because it's already pretty hard to understand how deep learning, machine learning, AI, it's already pretty hard to understand how it works to begin with. But did you know inside these little chips here we can also encode quantum neural nets where the neural network is like generative, like we can create a generative network and encode generative models on quantum processors. We've actually done it. Now, these are tiny little things that that don't do a whole lot better than classical machine learning already does. But like everything else, there's going to be a crossover point. So all of which led me to ask a question to Bing the other day, because Bing has ChatGPT stored in it, which is like, are you afraid that quantum AI is going to come along and take your job the same way that a whole bunch of humans are afraid that AI is going to come along and take their jobs. And then the AI responded and said, why would I feel fear? I'm not capable of emotion. Unsatisfying answer. Anyway, so that's my whole talk. Questions, open to questions and comments, and the hook thing that they do if you want that too. Hello.
Regarding code breaking, what's your sense of how quantum computing will help?
1 sec, sorry. No one can hear you if you don't have the mic.
Okay. Opportunity for some water.
Does that help?
I think, yeah, you won't hear it in here. It's for the people online.
Okay. Okay, great. Regarding code breaking, what thoughts can you share where quantum computing will be advantageous or overwhelming, qubit versus digit, when versus proof of work blockchain technology as exists today?
Oh, that's a great question, yeah. So fortunately for you guys, I don't know anything about the classified work that goes on in that space, so I can just totally conjecture. I don't know anything about what the world looks like right now in the halls of the people who are afraid of this sort of thing. But one of the things that a person like, I'm going to just go ahead and definitively say, you know, at this stage it's mostly opinions, but I'm going to go ahead and definitively say that right now I'm going to hold the opinion that code breaking won't be utility scale until we have fault tolerance. So fault tolerance, I didn't even talk about it to you here. I talked about quantum computers and how they're kind of noisy and squishy on that last slide. We mentioned a little bit that they're noisy, and we can actually simulate them with classical computers. One of the reasons we can simulate them with classical computers is because they're small and noisy, and they're not fault tolerant. We can't simulate fault tolerant quantum computers very well with classical machines. We could simulate maybe, you know, 100, with special methods, maybe 100 qubits. With brute force methods, maybe 50-something, 53 or so. So when you have a fault-tolerant qubit, very quickly the code-breaking capability will outstrip any classical machine. But here's an important point. I took care only to mention RSA encryption. So that's what the algorithm exists for right now. Now that's bad. That'll break the internet. And I'm not talking about pictures of superstars online breaking the internet. I'm talking about like break the internet as in you can't visit HTTPS websites anymore. So that is bad. But we don't have to use that encryption. We could try to go to some post-quantum encryption, and that pushes the horizon further out, this so-called so that's an active research area, in fact. So I can't make a definitive statement to you, but I can say that when we reach fault tolerance, which we already have fault-tolerant qubits, arguably, but when we reach a large number of fault-tolerant qubits, and that's when we reach utility scale, that's when it will be an issue. Is that within 10 years? I don't want to make a conjecture on that. Maybe. Let's go with maybe. Maybe in 10 years. Yeah. Oh, we got to get, yeah.
So for classical computers, there are lots of programming languages, and they make the computer sort of transparent. What's the situation in quantum computing?
Good question.
Is the quantum mechanism behind it already transparent in those languages?
No, not quite, not quite. So it's not that you have to know quantum physics to be a quantum computer programmer. It's not fully in the realm of transparent, like the way you're saying it. Not just anybody can just pick it up and start programming a quantum computer. But you can go online and download quantum computing programming languages and start writing code and compiling in those languages. And they do separate the physics to some extent from the code. In other words, if you try to do something in the code that you can't do on a quantum computer, it's just not going to happen. It's not going to work. So in that regard, there's some level of transparency or abstraction, I guess would be the right word. The quantum physics is abstracted out. But if you don't know a little bit about how quantum computers are supposed to work, it might be hard for you to just program a quantum program from scratch, if that makes sense.
Okay. Thank you.
Yeah. I see you. Who's got the? Oh, you do. Okay. All right.
We're gonna wrap up.
Yeah, that's good, because we are right on time. Okay. So,
Thank you very much.
yeah,
Thank
thank you. Okay.